Introduction to Hypothesis Testing. Identify significant results with probabilities, the rare event rule for inferential statistics. If, under a given assumption, the probability of a particular observed event is very small and the observed event occurs significantly less than or significantly greater than what we typically expect with that assumption, we conclude that the assumption is probably not correct. Let's take a look at example 2, body temperatures using table A-2. Now, assume that the population of a human body temperatures has a mean of 98.6 degrees Fahrenheit, as commonly believed. Now, also assume that the population standard deviation is 0.62 degrees Fahrenheit, and this is based on data set 5 body temperatures in Appendix B. A sample of size n is equal to 106 subjects was randomly selected, and the mean body temperature of 98.2 degrees Fahrenheit was obtained. Now, if the mean body temperature is really 98.6 degrees Fahrenheit, find the probability of getting a sample mean of 98.2 degrees Fahrenheit or lower for a sample size of 106. And then based on the result, is 98.2 degrees Fahrenheit significantly low? And what do these results suggest about the common belief that the mean body temperature is 98.6 degrees? Well, let's first draw our bell curve. So the first thing we want to do is draw our bell curve. So there's our bell curve, and then we want to be able to then label all the information that we want on there. So in this case here, we know that the mean, or the mean of the sample means, is equal to 98.6. Okay, and we want to find out the probability of getting a sample mean of 98.2 degrees Fahrenheit or lower. So that means we're going to be going over here to the left. We know that the sample mean is going to be 98.2. And so we're looking for the left, so we're looking for the area that's to the left of that. Okay, so again, that represents the X, which is the temperature scale. Below that, we're now going to write the Z scale. And so that means that when we use the mean, we know that the mean for the Z-scale is always going to be 0. And what we want to do is we want to find out what is this Z-score associated with the 98.2 degrees Fahrenheit. So we've drawn our bell curve and we labeled it. And now it says work under the assumption that the population of human body temperatures has a mean of 98.6 degrees Fahrenheit. We weren't given the distribution of the population, but because the sample size n is equal to 106 exceeds 30, we use the central limit theorem and conclude that the distribution of sample means is a normal distribution with these parameters. So we know the value of x, or the value of x bar in this case, or the value of x, is 98.2. We know that the mean is 98.6 of the sample means. We know the standard deviation is 0.62, and then n is equal to 106. And so what we're going to do is we're going to plug these values into our formula. So we have x, which is 98.2, and then we're going to subtract the mean, which is 98.6, and then dividing that by the standard deviation divided by the square root of n, and n is 106. So if we want to use our calculator to find this, we would do the following. So using our calculator, we're first going to go ahead and input the numerator. So we have 98.2 minus 98.6, which gives us negative 0.4. Then we're going to divide that, put in parentheses, we have 0.62, and then we're dividing that by the square root of n, which is 106. Move to the right, and then with the parentheses. and then we should get the following: negative 6.642, and rounding it to 2 decimal places gives us negative 6.64. So if we refer to table A2, we find that Z equals negative 6.64 is off the chart, but for the values of Z that are below negative 3.49, we use an area of 0.0001 for the cumulative left area up to Z, which is equal to negative 3.49. We therefore conclude that the region is 0.0001. Let's come back up here and then label what this is going to look like in our graph. Okay, we know that the z-score is negative 6.64, and we determined the area here is 0.0001. It's always good to go back and reflect on your graph. Okay, so the interpretation, so the results shows that if the mean of our body temperatures is really 98.6 degrees Fahrenheit, as we assumed, then there is an extremely small possibility of getting a sample mean of 98.2 degrees Fahrenheit or lower when 106 subjects are randomly selected. University of Maryland researchers did obtain such a sample mean, and after confirming that the sample is sound, there are two feasible explanations. One, the population mean really is 98.6 degrees Fahrenheit, and their sample represents a chance event that is extremely rare. And two, the population mean is actually lower than the assumed value of 98.6 degrees Fahrenheit, and so their sample is typical. Because the probability is so low, it is more reasonable to conclude that the population mean is lower than 98.6 degrees Fahrenheit. So in reality, it appears that the true mean body temperature is closer to 98.2 degrees Fahrenheit.